Alrighty guys, I'm going to introduce Lewis structures to you guys somewhat quickly. And the reason I'm doing this is so when we go over the next chapter, we're talking about carbohydrates, lipids, nucleic acids, all those different macromolecules we're going to study. It'll make more sense as the diagram I'm going to show you. Okay. So basically I'm going to show you Lewis structures. Now, where does all chemistry happen? Well, you should have said the electrons. More specifically, a better answer would be the valence electron, the electron in the very outermost. Now remember, when we talk about Lewis structures, we're talking about elements that are covalently bonded. So when I say covalently bonded, I mean both elements are to the right side of the stair step. Okay? Non-metals. That's also called a blank. Hopefully you said the word molecule. Because if they're the right side of the stair step and they're bonded together, they're sharing electrons. They want to become noble. They're sharing those electrons to become noble. Whereas if you have one from here and one from here, one from the right side of the stair step, one from the left side of the stair step, that's an ionic bond because they're stripping it, right? An electrostatic attraction. So remember, covalent bonds, Hippie bonds, sharing electrons, covalent, co being two, valent, sharing the valence electrons. Alright, so remember, when I say these Lewis structures, we're only talking about things to the right of the stair step. Remember, and hydrogen, because hydrogen and helium are, and you should have said weird. So, let's go ahead and start with electron dot notation first, because that's where we're going to start. So I'm going to start with the easiest element, hydrogen. One proton, one electron. Doesn't even have a neutron, typically. There are some isotopes that have different number of neutrons, right? To review, hopefully you already knew that. So, if I have hydrogen, we know hydrogen has one proton and one electron. So if I want to do a electron dot notation for that, I just do here. Now this one works out well because that's all electrons it has, but it only has one valence electron. Remember? So this dot right here, this dot represents the valence electrons. We don't care about anything else except for the valence electrons because that's where the chemistry happens, right guys? So that's what the dots stand for. So, now, another one, okay, so in a review, the reason these are grouped together is because they all have the same number of valence electrons. Hopefully you have another periodic table that is blank, and you know that all of these have one valence electron, all these have two. Don't worry about any of these. These have three, these have four, these have five, these have six, these have seven, and these down here have eight. Remember, this guy only has two because that first outer ring only fit two electrons. Remember, hydrogen and helium are weird. You should see a theme here. They're an exception to the rule. Alright, so everything must be noble, everything must be stable, everything here must have 8 electrons. Alright, so we did hydrogen. So let's do another one real quick. Let's do helium. So helium, right here, it has 2 valence electrons. Easily enough, it would just be like this. Helium, 1, 2. Why wouldn't I write this? Well, these are electrons. These are representing electrons here. Electrons are negative. They want to get away from each other. And, you could write it like this. That'd be okay too. Because they want to get away from each other. You could write it like this. I don't really care. Okay, I just need to know there's 2 there. So, but this technically, you want them spread out first. You don't want that happening. Because you want them to spread out. You can only have 2 there though. Correct? Alright, let's do another one. Let's do neon. Okay? Let's do neon. So we go back to our periodic table, we have neon here. So neon has, well, it has 10 protons, 10 electrons, but we don't care about how many total electrons it has. We only care about how many valence electrons it has. So if you look, you have 1, 2, 3, 4, 5, 6, 7, 8. All of these from here down are going to have 8 valence electrons. So I know that neon is going to have 8 valence electrons. So I can go 1, 2, 3, 4, 5, 6, 7, 8. Notice, neon stable, it's full. It's not going to react to anything because it has those 8 electrons. Okay? And this brings me to a good point. This brings me to what they call in chemistry the octet rule. Okay? What that rule is, you need to know this rule, is kind of important. All elements except hydrogen, right? Because hydrogen's weird. Okay? Except hydrogen and helium if you want to, but helium only wants to have 2, so we're not going to worry about that. But just all elements except hydrogen and a few others. I'm not going to. There are exceptions. I'm not going to make you know those because that's just going to confuse you. And a few other elements. All elements except hydrogen and a few other elements want 8 electrons in their outer shell. Okay? So remember, every element except hydrogen and a couple others I'm not going to ask you about. So for our purposes, every single element is going to want to have 8 electrons except for hydrogen, because hydrogen is weird. It only needs one more to become noble. It only needs to have one more electron, because that first ring, remember, only can take 2. Okay? This is an important rule to know, the octet rule. Nobility, octet, 8 electrons, stable, noble. Alright, let's move on. So, we have that. Let's just do one more of these electron dot notations just to make sure we're clear with this. Okay? One more. So this is the electron dot notation. So I have carbon. I have 1, 2, 3, 4 valence electrons. So to draw that real quickly, 1, 2, 3, 4. Alright, we got that. I'm beating a dead horse here. Probably should say it in horse country. So, now let's move on to, let's do a compound. Let's draw a little structure. Okay? So, I'm going to do a very simple one. H2. So, hydrogen gas. So, H2. Now, if we want to do it, so we have a hydrogen, now we know it only has 1 valence electron, right? Because 1 valence electron here. So, we have 1 here, and then how many do we have? We have 2 of those hydrogens, right? So we have 1 here. I'm going to represent this by an X so you can just see it for me, okay? So now I'm representing both of those because they both have 1 valence electron. So what happens is they want to share that electron. They're going to share it because they are both nonmetals. They're going to covalently bond. They're going to share those electrons. So what's going to happen is we're going to have this. So we're going to have these guys sharing this electron here. So guess what? They both have their outer ring full. Another way of drawing that is this. So anytime you see 2 dots, or okay, this could also be rewritten like this. Most of the time in textbooks you'll see it written like this. That represents 2 electrons that are being shared. That can be represented by an electron by this dash right here. This dash takes place of 2 dots. So 1 dash equals 2 dots. Okay, or 2 electrons. So this is an electron pair. A better way of saying that actually is just call it an electron pair. So 2 electrons. Okay? So another way of saying that are 2 electrons. They're sharing. Alright? So this would be an example of a non-polar. Doesn't have a pole. They share it equally. It's a perfectly hippie bond. They are sharing in complete harmony. Because they have the same electronegativity, they're sharing those exactly equal. Alright? So let's do another one. Let's do let's do fluorine. So we're going to do fluorine here. So we have fluorine. So all these have how many valence electrons? Well, you should have said 7. 1, 2, 3, 4, 5, 6, 7. This has 8. They're 1 away. Alright? And fluorine should also know is the most electronegative element in the universe. It wants electrons real bad. Alright, so let's do F2. Alright? So, what you can do is you look at this, you know that there's 7 electrons around this, correct? So, we have, draw it like this. So we have 1, 2, 3, 4, 5, 6, 7. Draw another one. We have 2 of them, right? That's 1. This would be 2. 1, 2, 3, 4, 5, 6, 7. Now, you're probably going to see where there's a spot left over. There's a spot here, and there's a spot there for a dot. Now, where they're at, it's arbitrary. It does not matter. So you can kind of shift these around. Remember, these electrons are moving all the time. So we're just kind of showing you a visual representation of this. So this guy, they're going to want to bond like this. So I'm going to draw these guys with X's here, so make it a little bit easier to track. So I'm going to refollow this with X's. All right. So then we have here. I'm just going to put here, 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 here. Same idea, right? 1, 2, 3, 4, 5, 6, 7. Still have 7. I'm just rearranging this one down here. So I'm going to rearrange this one down here. So here we have this. We have 1, 2, 3, 4, 5, 6, 7. Alright, so now you can see the difference between this element and this. They're sharing those electrons there. Now, another way of drawing that is this. Now, check this out. this has to have 8 electrons, this has to have 8 electrons. This is important. This is the octet rule. These guys are sharing these electrons, right? There should be 2 here. So 2, 4, 6, 8. We have 8 there, right? So we have 2, 4, 6, 8. We have 8 over here, right? Good. Then we know we did it right. So if I double check here, 2, 4, 6, 8, they're sharing these, so there's 8 electrons here. 2, 4, 6, 8. I have 8 electrons there. Okay? So now we're kind of seeing an idea here. All right? This would also be nonpolar. This would also be a nonpolar because they're sharing the electrons equally. All right? They're sharing those electrons equally. All right. Let us do another one. So another way to double check your answers, you got to make sure they all have 8. You make sure you have the octet rule. All right? You got to make sure they all have 8 electrons here, except for hydrogen, right? Because it's weird. And then what you can also do is you can see that fluorine has 7 electrons, right? Because we know that because this is 8, this would be 7. 1, 2, 3, 4, 5, 6, 7. So basically we have fluorine. How many do we have? We have 2 of them, right? There's another way of doing this to write it out of time. Times 7 electrons in each, that equals 14. So when I finish here at this stage, I should have 8 in each atom should have 8 electrons, and total summation I should have 14. So look, 2, 4, 6, 8, 8 there. 2, 4, 6, 8, 8 there. But in total, law of conservation of mass says I can't make up electrons, so throw them away. 2, 4, 6, 8, 10, 12, 14. Oh sweet, they matched. That must be correct. So this would be the finished product right here. So this would be your finished product of your Lewis structure. They call these, so these are bonds, chemical bonds. These are lone pairs, okay? They're not being shared. They're by themselves. They're loners. They're alone. All right? Let's do another one. Let's do a little bit more difficult. Now, there's another rule I'm going to show you guys. Okay? How I remember this is anytime you see carbon in a Lewis structure, so if you have a molecular formula that has carbon in it, typically put it in the center. Okay? Now, how I remember that? We are carbon-based life forms. Carbon's in the center of our life. So we're carbon-based life forms. So a thing to remember. So this is a rule you may want to know. So carbon, hope you guys can read this, is often the central element in a Lewis diagram. Okay? And also, if you don't have carbon there, what you can do is you can do the elements with the lowest electronegativity. Okay? Negativity. So the one with the lowest electronegativity is usually, usually the central atom. Okay, that may confuse you. The main thing I want you to know is that carbon is the central element. If you're having that, if I give you one with carbon, it's probably a central element. All right. So remember, the most electronegative element in the universe is fluorine. So these are all pretty electronegative. They want those electrons real bad. As you go this way, they get less electronegative. Okay. They don't don't even want the electrons. They want to get rid of their electrons. They're not electronegative, not nearly as electronegative as these guys, because they want the electrons real bad. These guys don't want electrons. They want to push them away because they're one away from being noble. All right. So let us do this. Let's do this molecule. Yeah. CH4, methane, I believe. Hopefully I didn't say that wrong because this is going to be burned in eternity on the YouTube. But let's do CH4. Pretty sure it is. So we have. So now instead of drawing it, you can draw it out each time. I kind of find that. I mean, you can do that. This guy has. So carbon has how many valence electrons? I'm going to do this once. 1, 2, 3, 4, right? So you can do this. 1, 2, 3, 4. I kind of find this a waste of time. Hydrogen has 1. Okay, so that's what you have right there. That's electron dot notation. I don't see a point in that if you understand it, but if you want to draw it out, by all means, you're welcome to. So now what I typically do is I go to this. So I got this information from P to the T. Carbon has 4. 1, 2, 3, 4. Hydrogen only has 1. So I do this. This is what I have most students do. Okay. So carbon has, like I just said, I have 1 carbon, right? Just one of them here, right? Understood to be 1. And it has 1, 2, 3, 4 valence electrons. I got it from looking at this. 1, 2, 3, 4. So it's times 4 electrons, that equals 4. Okay. Hydrogen, I have 4 of them. They have 1 electron each. That's going to equal 4 electrons. Okay? Because look, hydrogen only has 1, so I summarize these, so in total I should have a total of 8 electrons when I'm finally finished. So I should come back and check that when I'm done. So carbon, I'm giving carbon, it's a central atom. Anytime, and also if you're ever confused, the one that there's least number of is probably going to be in the center. So if you have if you have like 2 or 3 of something and they have 1 of something else, that's a good way of eliminating things. So I have C. How many H's do I have? 1, 2, 3, 4. Now, what you could do is you could do this and then put 1 around it, but there's an easier way. You know from the octet rule, right? That for carbon to be noble, it needs to gain 1, 2, 3, 4 electrons, right? For this bond to form, it's going to have those 8 electrons. It has to. It's the octet rule. So what you could do is this. And how many does hydrogen need? Only 2, because it only needs 1 electron to be like helium. Because this only has 1 electron, this only has 2 electrons. So the first ring only has 2, remember? So now, you can just do this. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so now, make sure I satisfy my octet rule. Does this central carbon atom have 8? 2, 4, 6, 8. Yes, it does. Does the hydrogen need 8? No, it does not, because this weird only needs 2. So that's satisfied. And the last step I need to do is to make sure these match up. 2, 4, 6, 8. Oh, wait, it matches up. I haven't made up any electrons out of thin air. Another way of drawing this again is like this. Boom, 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 boom. Same exact thing here, but this is the more precise way of drawing it. This is the way you'll see it in textbooks. Okay? This is also a non-polar. They are sharing equally. I'll explain more of this later. So this is non-polar. Alright? This is the Lewis structure of this. Okay? Remember, 2, 4, 6, 8. Remember, these represent 2 electrons. It's important. 2, 4, 6, 8. I have 8 there. These guys are satisfied 2 here, 2 here, 2 here, 2 here. Everybody's happy. Okay? Everybody's happy. Let's do another one. Let's do carbon tetrachloride. Alright? Carbon tetrachloride. So, and the reason we're doing this is so when you see these molecules next chapter, it'll make more sense to why they're organized the way they are. So now we're going to go to carbon tetrachloride. So, I'm going to write it right up here. I'm going to write CCl4. Okay? So carbon has 1, 2, 3, 4 valence electrons. So I'm going to write carbon equals, there's 1 here, right? 1 times 4 electrons equals 4. So we have chlorine. Most students make a mistake. They skip this step. They do it in their head. If you can, that's fine. But I'm telling you guys in mathematics, the less stuff you write down, the greater probability of you making a mistake. All right. So I have 4 of these. This is where most students, they forget to bring that down. They forget to bring that number down there, and it messes them all up. So if you ever mess up and you're like, something's not right, that's probably what you did. Chlorine has 1, 2, 3, 4, 5, 6, 7. Has 7 valent electrons. Okay? Alright, so we have that. So this guy has, multiply that, 28 electrons. So when I'm done, I should have a total of 32 electrons. Valent electrons. Okay, we're not worried about anything else with the valent electrons. So, here's what we're going to do. So we have carbon. It's in the middle. You can probably already see what's happening right now, guys, right? It's getting like, oh, okay, this isn't too bad. So I have a carbon in the middle, right? Carbon-based life form. Cl1, Cl2, Cl3, Cl4. Now, you could count them all up and do it, but I tell you guys, this is the way to do it. Octet them all, okay? Put 8 around all of them, all right? Because these all have to satisfy the octet rule. They all want to be stable. This guy wants to be noble, right? These are halogens. They only need 1, okay? These guys need more, so put this guy in the middle because we're central atoms, so we just octet them all. 1, 2, 3, 4. So I'll get back in a second. So I have 8 here, but this guy needs 8 too, right? This is where it gets kind of important to double check your work here at the end. And I'll explain in a second. So this is a little bit further. This top one here needs to be pushed down a little bit further, but you get the idea. Alright, so now what I do is I make sure everybody has 8. So 2, 4, 6, 8. Here we go. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody has 8, everybody has an octet, everybody's happy, everybody's noble, everybody's sharing. Right? Now I need to count all of them. So the way I do this, a lot of students make a mistake, I count the inner one first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 28, 30, 32. Oh wait, I have 32 electrons. Awesome. That matches that. I am done. Okay? Not really. I have one more step to do to simplify this. So I can just do C, Cl, 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 Cl. Okay? And in the textbooks, they don't really write the those lone pairs anymore, but we're going to write them with Lewis structures here. So now I need to put these here. Okay? Because now, okay? So now everybody's good. So now everybody has, remember, 2, 4, 6, 8. Those are representing 2 again. Okay? So now I should have a total of 2, 4, 6, 8, 2, 4, 6, 8. I've done this all earlier. I have 32 electrons here. Okay? Good? Not bad. Also, this is a nonpolar. This is nonpolar also. Okay? This is nonpolar. Alright, let's do another one. Let's do one that is not as straightforward here. Okay? Let's do this one. CH3I. Okay? So I'm not going to draw them all out because you can figure this out, but I'm going to break them down one at a time. So C, I have one of them. The carbon we know has 1, 2, 3, 4 valence electrons. Times 4 electrons. That equals, okay, 4. Hydrogen, I have 3 of them, right? So we have 3 times 1 electron equals 3 electrons. So then we have iodine, I have, let's check it out, iodine right here, okay? That has 7 valence electrons, right? So we have 1, 2, don't count the transition metals, 3, 4, 5, 6, 7. But I have one of them, right? 1 times 7 electrons equals 7 electrons. Don't make a mathematical mistake. It should be a total of 14 here. 14 electrons. Okay, now, what's the central atom? Well, it should be carbon, because it has a lot to give. Because carbon has 1, 2, 3, 4. It has a bunch of different sides it can use. So you should be able to see this in your head now a little bit. So I put carbon in the middle, put a hydrogen here, hydrogen here, hydrogen here, iodine here. Now, depending on where you put it, it does not matter for our purposes. It does not matter at all. I don't care. So you can put the iodine here, wherever you want. Alright? But it just got to be connected to the carbon. So then I octet everything, right? Now, I have to octet this guy because this still needs 8. Okay? These guys don't, because they only need 2 to become noble, right? To have an electron configuration of helium, to be a noble gas. They still have the same number of protons. Remember, we're not changing the number of protons, we're only messing with the electrons right now. They're sharing. Okay, so let's double check. So we have 2, 4, 6, 8. That guy's good. 2, 4, 6, 8. They're good. 2, 2, 2. Now, see the sum 8 to 14. The whole thing got the sum 8 to 14. 2, 4, 6, 8, 10, 12, 14. Sweet, we're done. So you just draw it like this. H, H, I, H. But I'm not done here. I got to put the valence electrons around it. So this would be the Lewis structure. This would be a polar molecule. Okay? Do you see why? There are more electrons here than there are here, here, here. So this side is going to be slightly negative, and these sides would be slightly positive. Okay? All slightly positive, slightly positive, slightly positive. Okay? So that's why it's a polar molecule. They're not sharing completely equally. Alright? So let's talk about water. We're going to do water real quick. Let's do water. And with water, we know oxygen has 1, 2, 3, 4, 5, 6. Okay, it's 2 away from being noble. So let's do water real quick. So water. So now, I have 2 of these, 2 hydrogens. Right, I have 2 of them right here, times 1 electron, if you know that. 2 total. Oxygen, I have 1 of those, times, and oxygen I have 6 electrons, remember, looking at the P to the T. 6, so this has a total of 8 electrons. That's the number we want to plug it in with, right? So, now, because remember, we have 1 here, we have 1, 2, 3, 4, 5, 6. So 6 and 2 is 8, good. So now if you have two of these, one of these, like remember these can't bond with each other because they only have one electron to share. So this would be in the middle, this would be on the outside. Now, so what does this guy need? He needs 8 electrons, we know, right? So go ahead and octet it up. Now, so here we go. So now I have 2, 4, 6, 8, good. 2 here, everybody's happy. Everybody's noble in their electron. Now, but you notice, so if I draw it like this, okay? So this is the way a lot of students draw, but the molecular biology is a little more complicated. I would take this on a Lewis dot structure, but it's not technically correct because you get into the Vesper model. We're not going to get into the Vesper model, but what it actually looks like, and as you guys are well aware now, we have a like this. Now the reason it's bent, because these electrons are up here. These guys are sharing electrons on a different plane. This we're getting to, we're getting like the 3-dimensionals. I'm not going to get into that, but why it's bent, because these electrons are going to get away from these guys, okay, because remember this has a proton in it, and these are trying to get as far away from those as possible, and the electrons are sharing here, and they try to get as far away from each other as possible. Now, don't worry about the molecular reason as to why this is bent. It gets kind of complicated. Just know that these electrons are up here, so remember, this is slightly negative, right? And these sides are slightly positive, right? So slightly positive, slightly positive. I have more electrons here than I have here. So that's why it's a polar molecule. We have ends, we have poles, okay? Because we have electrons up here, all right? And they're not sharing equally, all right? Let's do one more I'm going to talk about. I'm going to do a couple more and then we'll move on. Now, there's double bonds. We're going to talk about double bonds. These have been pretty simple so far. You're like, why do you always go back and double check at the end, Mr. Smith? That seems weird. It seems like a waste of time. I don't need to do that because it's going to always be the right number. No. So double bonds form, well, let's put up, double bonds are form or found, are found between carbon, nitrogen, oxygen, and sometimes sulfur. I'm going to do an example of sulfur, so I put it in there. But if you see these guys that are bonding to one another, a lot of times they can have double bonds. What are you talking about? Well, let's work an example that's kind of hard, right? Yeah, I'm sure looking forward to it. Now, the diatomic molecule, 78% of our atmosphere, is made up of, you guys said nitrogen. Very good. All right, you're listening. So, nitrogen. So, let's do it. Nitrogen has 1, 2, 3, 4, 5 valence electrons. Let's do it again. 1, 2, 3, 4, 5 valence electrons. So I have we have 2 of them. We have 5 valence electrons, okay? That's going to equal 10 electrons. So that's what we should get when you're done at the very end, correct? Alright, check this out. So I have one N. I have another N. Now, you know both of these have to have the octet rule. They need 8 electrons around them, right? So let's go ahead and do it. You're probably going to see this already. Okay? Alright, good. Everybody's got the octet. 2, 4, 6, 8, 2, 4, 6, 8. Perfect, right? No. Check out, last step. 2, 4, 6, 8, 10, 12, 14. What? I have 14 electrons? I just made up electrons. That is not right. That is too many. I have 4 too many electrons. Okay? I have way too many electrons. So what you can do, alright? So what you can do, I draw this again. I'm going to show you. So you can remove a pair here and remove a pair here and just put them in the middle. Okay? So to show you again what I just did, I removed a pair here and here, and I would put them right there. That's a double bond. So let me show you that again. So all I'm doing is I'm removing these two, right, because they're going to share. So now I have those. I'm going to put those right here. I'm going to redraw that as here, 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 here. Then we have boom, 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 boom. Okay? So now they're sharing both of these now. They're sharing all 4 of those electrons. Okay? So now I do it. I have 2, 4, 6, 8. 2, 4, 6, 8. Octet rule is good. Let's check it again. 2, 4, 6, 8, 10, 12. So now I have 12 electrons. Huh. Still too many. How many can I have, says law of conservation mass? Only 10 valence electrons. So what I do again, same idea. Erase here, put it here. Okay? So once I do that, let's do that the last time, so I'm going to redraw that here, 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 here. This is a triple bond, right? So then we have here, 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 here. Now, so that is, so let's check it out. 2, 4, 6, 8. They're sharing. We have 8 in their outer shell. They're good. Do I have a total of 10? 2, 4, 6, 8, 10. I do. So another way of writing this would be this. Okay? So now, I have 2, 4, 6, 8. 2, 4, 6, 8. Octet rule satisfied. 2, 4, 6, 8, 10. So this is the final product of that Lewis structure. Don't worry, they're not all that crazy. But this is why you have to double check, especially if you have a carbon, nitrogen, oxygen, or sulfur in there. You've got to double check that. Alright? So let's do, okay, one more I was going to do for you guys. Let's do the example, yeah, right here. Alright, so now, I'm going to do sulfur trioxide. So, let's go ahead and do, this is the last one I do. Alright? So remember that octet rule, carbon's essential atom, halogens, the ones that are in this group here, you don't have another halogen, but the ones that only need one electron to become noble, they are going to typically be on the end. They're going to be on the edge. They're going to be on the outside, the perimeter, the periphery of the element because they only need one to become noble. So let's do this one. SO3. Okay? Now, so now I want to look at S, sulfur. 1, 2, 3, 4, 5, 6. 6 valence electrons. So I'm going to do S equals 1 times 6 valence electrons equals 6 electrons. And then we have oxygen. You have 3 of them, right? 3 right there. So we have 1, 2, 3, 4, 5, 6. So this is 18, right? Pretty good with that. These are valence electrons, remember? So now we need a total of 24 electrons. Valence electrons, I should say. So, now, we're going to put, so since there's 3 of these and 1 of these, which one do you think goes in the middle? Yeah, very good. If you said sulfur, you're good. So sulfur, now, good. So then I'm going to do an oxygen here, an oxygen here, and an oxygen here. I'm going to octet them. So boom, octet this guy, good. Octet, octet, octet. I need a pair right here. Okay? So, now I know the octet rule is satisfied. Let's check it out. Remember, the way I count these, so I'm confused, I count the center one first, then I never count the inside anymore. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Ah, I have 26 here. Does everybody understand what I mean by that? I count this one first, and then I never count the inside again. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. It's the easiest way. A lot of students have problems because they don't know how to count it without recounting stuff. That's the way I found it's the easiest. So now I have too many electrons. Alright, so I need to basically double bond one of these. Does it matter which one? No, it does not. Okay? So I'm going to take this pair of electrons off. Okay? I'm going to add a pair of electrons here. Okay? So let's take a look at this. Let's check. Okay? Let's check see if I have too many. So let's see if I did this right. But I think you may have seen a mistake I just did. I'm going to do it intentionally. So now I have this. I have S, boom, boom. This is why you have to double check everything, guys. So now, so here I have double bonds, right? So I'm showing the double bonds right here. Here. Then I have okay, so I had 26, let's see. Remember, if you saw me just erase it here and put it there, you know I should have the same amount of electrons, right? So 2, 4, 6, 8, 2, 4, 6, 8, 10. What? There's 10 here. Check it out. 2, 4, 6, 8, 10. That's too many, okay? So let's just do the whole thing. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Still 26. What I didn't do is I took one off this. I didn't take one off here because remember they're sharing those. So what would happen this, I would take this guy off, okay? So now check this out. Because the only one that was, everything was good, I had too many electrons, and then the way you can double check that, which one has more than 8 electrons, because that's what will happen. Because that one had 10 last time. So, let's check it out again. 2, so 2, 4, 6, 8. Oxygen here is good. 2, 4, 6, 8. 2, 4, 6, 8. Sulfur is good. So you see it? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Sweet, I'm done. So now, and also, just double check this again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Huh. I have 24 here. I have 24 there. That's why you have to do that, guys. You have to double check these things. Now, another way of writing this is like this. Sulfur, right? 2 light right here. Boom, 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 boom. And every time you draw a new one, just double check, take the extra 30 seconds. 2, 4, 6, 8, good there. 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Good, I'm done. Okay? Hopefully you guys got something out of that. Remember, these are molecules. These are covalently bonded, right side of the stair set. We cannot draw Lewis structures for ionic compounds. We don't do it because they don't share like this. They're stripping. We don't draw them for this. Okay? That's an important thing to take home. We're only dealing with the valence electrons. Remember, the number of protons here stay the same. We're not worried about it. So where's the chemistry happen right now? We're talking about the valence electrons, the outer shell. Okay? The very outer shell. Hopefully that helps. If you have any questions over any of these, please feel free to ask on where you're stuck. Alrighty guys, have a good one.